This is StarTalk.
Welcome to StarTalk. I am Dr. Natalie Starkey, and this is StarTalk All-Stars. Today, I'm going to be your all-star host, and joining me as a co-host, I have comedian Chuck Nice.
Hey, Natalie. Well, Natalie.
Natalie. Nice to see you.
Good to
Thank
see you
you
too.
For coming in.
Always a pleasure.
So today the plan is to field some fan questions about our topic today in, the cosmic queries.
Yes.
We're going to be looking at the topic of the Rosetta mission.
Yes.
Really exciting.
It very much is an exciting mission.
Very close to my heart because
I'm
it's
sure it is.
kind of what I've been doing for my research the last few years. And so I'm excited to talk about Rosetta, very excited. And I'm also more excited to introduce our guest today, joining us via Skype, and it is Dr. Matt Taylor.
Dr. Matt Taylor.
Yes, welcome, Matt.
Thank you for having me.
That's all right. Now, Matt, you are the project scientist for the European Space Agency Rosetta mission. This is quite an exciting title. I wish I had your job, but you are really, really busy. So I don't envy you for the amount of travel and talks you're currently doing. But it's so good to have you here.
It's my pleasure. It's my pleasure. It is a bit hectic at the moment, surely.
So explain to us, there's a lot going on, right? So we've had the Rosetta mission launched, over 10 years ago now, right? And it's been traveling to this comet. It was traveling to a comet for all of this time. It had to catch up with this comet, get onto the same orbit, which is no small matter in itself.
Right.
And then in 2014, it actually caught up with the comet, went into orbit around it. First time ever we've done this.
Yes.
And then not only that, a couple of months later, landed as spacecraft on a comet, which is just the best thing ever. And, first time we've ever done this. It was successful, a soft landing. There was a little bit of a bumpy ride until it came to rest. But, it's done science. It did its first science sequence as planned. And then since then, the little lander, little Philae lander, as it's called.
That's correct.
Is asleep. It's gone to sleep.
It's going to sleep.
Matt, what's happened to it?
Is that the scientist's way of saying that it's now on a farm with your grandmother? What do you mean when you say it's gone to sleep? What's happening? Don't you guys try to tell me something?
The problem with it, it's like Schrodinger's lander. We can't really tell.
I got you.
We can't go up to the comet and kick it to see if it's still alive. It's highly unlikely to be able to function anymore at the moment due to power limitations, due to the fact that it's moving away from the sun.
Right.
But yeah, as Natalie said, we carried out the first science sequence. We carried out the main part of the science. It did what it was supposed to do, which was to go into hibernation. And it's just because it did this extra little leap across the comet that it was put into a situation or a location where it took a bit longer to come out of hibernation than originally planned.
I think you guys were just being cheeky, though, because you were like, we want to land on a comet, but hey, wait a minute, we're going to land 3 times, not once, we're going to just do it all in one go.
Funny enough, one of the original lander proposals, I think this is by Helmut Rosenbaum, the kind of main father of the lander mission itself, was to have a comet hopper that was jumping around that would go to one place and then go somewhere else. And it was as if that ethos was somehow impregnated into the lander, that it wasn't happy enough to be in one place. It wanted to go somewhere else.
It knew. It was like, I like that proposal. Let's do that. I'm going to do it anyway. But it's kind of crazy because, comets have so little gravity. These things are relatively small compared to, one of the planets. So it's just really lucky that it didn't, on one of these bounces,
just bounce completely off and just go.
Yeah.
Right? It would, because that could have been a scenario where it bounced off and it would have been lost forever at that point, right?
Yeah, exactly.
Yeah.
There'd be no way of getting it. It had no power itself, the lander, so it couldn't have got itself back.
It couldn't have gone back.
Yeah, so that would have been bad.
It clipped one of the kind of cliffs or whatever you want to call some of the features on the surface of the comet. And I think without that, it had lost a little bit more momentum. And without that little clip that it made, it may have had a little bit too much momentum on one of the bounces and ended up going over the edge, and that was it. It would have been lost. So luck was there.
We were lucky. We got it. We got some science, which I'd love to discuss if we've got time today. But it's still there. But it woke up, right? The lander did wake up again was it July last year or something?
Yeah, it was June, July time period, but we never got a full accurate signal lock with it. There were some issues. We never really got in talking terms with it properly.
Right.
But It's important to know, I have to know that this isn't the only part of the mission. This gets forgotten, that the Rosetta mission is more than the 60 hours of data taking that we had with Philae, and the majority of the science is being done by the orbiter and remains being done by the orbiter.
Says the physicist, I have to point out, because all the physics experiments are on the orbiter.
Okay.
I'm a geologist, so I'm like, right, I want to be on the comet.
You want to be on the comet and pulling up samples and getting something back and
here's
getting
exactly
readings.
Right. The orbiter is still functioning. And,
all right, so Matt, with respect to the orbiter, what kind of data are you looking to receive? And as it orbits this comet on its journey, is it just primarily looking at the comet, or is it surveying the what's around the comet and where the comet is going? Are both of those things happening, or one of those things, or what?
It's doing both. Rosetta itself, the key aspect was that unlike any other mission we'd done before to a comet, we were going to stay with the comet. So as Natalie said before, we rendezvoused and we got in the same orbit as the comet. And we've been doing that for over 2 years now. So we got in step with the comet, and we've seen how the comet has evolved in time. As it gets closer to the sun, it was becoming more and more active, throwing more material off. We've been monitoring the comet, and we've been observing the comet, both the nucleus and the outer atmosphere, and how that actually, in addition, how that interacts with the outer atmosphere of the sun as well. So the whole 9 yards, that's what we've been looking at. We've really been the whole thing about the Rosetta mission is to study this comet as in-depth as possible. And with the lander, we get the ground truth of these measurements, but with the orbiter, we get the global view, and we match those together. That was the key aspect of this. We do the majority of the science with the orbiter, but the lander was there. Philae was there to get on the ground and give us the ground truth, to really dig in and let scientists like Natalie, who like to, dig and scrape in and sniff and taste things.
It's good.
She's always rolling around and playing in the mud.
But Matt, what I wanted to just mention is the end of the mission, because it's going to be a really sad time for all of us. I imagine more so for the guys that are really heavily involved on the mission side. But the end is coming. It's this year.
The end is near?
The end is very near.
Oh my goodness.
And there are some really crazy plans of how this mission is going to end. And it involves essentially crashing this orbiter that's doing all this amazing science with all these very expensive instruments on board, crashing this thing into the comet.
Okay, now that sounds, Matt, very much like when I was a kid, I would build a giant Lego castle and then kick it down. Why is that the end of the mission? What is going on with you guys?
I'm like, I've always wanted to break stuff, really expensive things. The problem we have is the comet is moving away through Keplerian motion. It's moving away from the sun. Now, the spacecraft is orbiting around or is in the same orbit. That's moving away from the sun as well, losing the capability of generating power. So we'll get to a situation where we would have to put it into hibernation. We had to do that before because it moves so far away from the sun anyway. And because of the orbit the spacecraft is now in with the comet, it would freeze. We're also running out of fuel. We'll have no fuel left soon. And the best thing to do was to end the mission in around September, October time. Actually, the reason for that is we get to a time where the solar energy is reducing, but also we go into a conjunction with the sun. So the signal that we're getting from the spacecraft is very minimal at that time period. So we kind of thought the end of September would be a good time to close the mission off. Now, we could have just switched the mission off, or do something more extravagant. And the more extravagant thing has been to carry out a controlled impact with the comet.
A controlled impact, not a crash.
Yes, exactly. That's what I tried to tell my insurance company about my last controlled impact with another car.
I love this idea because it means on the way down, the instruments are still going to be on, and they're going to get tons of information as they go down, because this will be the closest we've ever been with the orbiter, obviously, having not crashed it into the comet yet. They've done some amazing math. All right, I'm in the States now, I forget. Math. We've done some very clever math to work out how to orbit around this thing, because it's haven't really got enough gravity for an orbiter to just orbit.
Right.
Kind of
it's not going to be in a gravitational tractor pull.
A little little bit, but it's been in powered flight a lot of the time. So it's like, we don't want to get too close, but this comet is also active. So it's got material streaming off the surface. So you don't want to get that orbiter too close and be hit by dust
particles coming off of it.
This is like our best chance to get close, get some really detailed images of the surface. I think, 1 pixel, is that going to be a meter or better than that? Do we hope?
We'll get much. I think once we get to within 10 kilometers, we go sub-meter, 50 centimeters, 10 centimeters. We're going to get very high resolution images once we get down to that level.
Really?
Yeah.
And so as you take this, as you capture these images, and you're still in orbit around the comet as it's doing its controlled impact, are you going to be surveying all parts of the comet, like kind of going around it and taking pictures like a radial camera? Like, is that the case?
That final, what we're calling the last words of Rosetta, is actually still being, I wouldn't say discussed, is being calculated, because although this comet is very low density and has a weak gravitational attraction, it still has gravity. So the orbiter actually is now in a bound orbit. We're at about, I think it's a 26 by 20 kilometer orbit. We'll go closer and closer and closer. We'll get below 10 kilometers. And once we get to below 10 kilometers, things get very complicated because of this duck-like structure. And so we have a very weird gravitational potential once we get down to that. So we'll have to put it in a special orbit and really be careful at how we control the spacecraft around that time, and we will feel perturbations of that gravity, and we will be continuing to try and do as many measurements as possible once we get close by. Now, those final words, as we're talking about the last day of Rosetta, what we do there is still being discussed, still being fine-tuned. We believe it will be some kind of arresting maneuver from a close pericenter orbit. So we'll have like maybe an elliptic orbit that goes within about 1 kilometer, maybe at the surface, maybe even lower, depending again on what we're doing in September. And then we'll inject towards the comet and just set ourselves up to be able to take data as close as possible. Now, the priority will be the imager, but also the mass spectrometer to sniff everything as close as possible. We'll have other instruments operating, but when we start getting to low power during that period, we really have to say, right, these are the priority instruments, getting those images, getting the high resolution images, and also the high resolution spectra from this mass spectrometer that's sniffing the gas.
That does excite me. I love mass spectrometry.
And is there any anticipation as to what the comet will smell like? Because I'm hoping jasmine.
It is far from nice. We already know how horrible this thing smells. Yeah, there's alcohol on it. It's like a kind of a Friday night in a bar area in any city in the US or Britain or wherever. Are you
telling me this comet will smell like a drunken fart?
Yeah, pretty much.
Basically.
Yeah.
That's it. Yeah.
It's probably not a good place to be.
It smells like Jersey. I can say that. I lived there. Okay.
Chuck, we should probably move on to some of these fan questions because we've been nattering on about
that was a ton of fun, and honestly,
I want to get some questions.
Yeah, we should get some questions in, without a doubt. But I'm so happy that we had that conversation. Yeah. Because now I know that basically we spent $1 billion to find out that a comet smells like a fart. Quite frankly, that was worth my tax dollars.
Good.
Okay?
I'm pleased.
All right, guys, let us go to our cosmic queries, where we have taken questions from all over the internet and every different incarnation where StarTalk exists. And I am going to start off with Greg Fisher from Facebook. And Greg says this: are we planning any other missions to any other comets? Is there any specific interest in landing on one of the asteroids in between Mars and Jupiter, or in the Oort Cloud?
Oh, this is a great question.
That is a very good question, Greg.
Very good question. Thank you. I love this subject. There's so much to talk about, but I'll keep it fairly short. So we're not planning any missions to comets at the moment, unfortunately, but we are planning some missions to some asteroids. Now, these are not in the asteroid belt between Mars and Jupiter because it's quite a long way to go.
Right.
What we do is we wait for these asteroids to be knocked out of the asteroid belt and join us in the inner solar system. So these become near-Earth asteroids.
So now let me just, I'm not infringing on your question, Greg, but how do we know when an asteroid is going to get knocked out of the asteroid belt?
We don't know when, but I don't think we can tell when anyway, but I'm probably not the right person to ask. But we know when they have been knocked out, and we know we can trace the orbit, so we can observe them in space. And we have a whole list of near-Earth asteroids, and we have a list of those that are on potentially Earth-crossing orbits. These are the ones that we need to worry about, and we keep an eye on them, and we check, that we need to just really define the orbit really carefully and work out. And gradually these fall off the list because most of them end up not, as we work out a little bit more where they're going, they're not going to hit us. But there's a few that we want to go and visit with space missions because they're kind of easy to get to because they're already on a better orbit. We don't have to go as far. There's the NASA OSIRIS-REx mission, which is launching this year. It should be launching this year, and it's going to approach an asteroid called Bennu in 2018, I believe, and it's going to be collecting samples to bring back to Earth, which is probably just the second time that's happened. The Japanese had a mission called Hayabusa that did this a couple of years ago. I've worked on some of those samples, tiny little dust samples from this asteroid. But there's also the Hayabusa 2 mission, which is another Japanese one. It's already been launched, and that is going to another asteroid, near-Earth asteroid, and hopefully collecting samples again. So we have a couple that we're going to. In terms of getting to the Oort Cloud, collecting samples, that's not going to happen. It's just so far away. Again, we need to wait for one of these comets to be knocked into the inner solar system for us to go to it, like we did with Rosetta in 67P. It came to us, so it makes it a lot easier. The Oort Cloud is just an immense distance away that it would be. Yeah, we'll never get there, I don't think. Not in our lifetimes.
All right. Oh, well, Greg, that is a great question, because this is a cool question.
Do you know what, Chuck? We actually need to take a break.
Okay, well, then I'm not going to read this then.
Can we come back? Can you save it till after the break?
No, that's it. You've ruined the show,
We've ruined it now. All right, okay, so we are going to take a short break, but we'll be right back with StarTalk All-Stars. Welcome back to StarTalk All-Stars. I am Natalie Starkey, and I still have here with me Chuck Nice, who's going to be asking me some more cosmic queries. And I've got Matt Taylor on hand from the European Space Agency to help answer some of the questions if I can't answer them.
Absolutely. So let's jump right back into our cosmic queries, and let's go to Josefina Acchiero.
Same again.
Yes, Acchiero in Waltham, Massachusetts.
Okay.
And Josefina wants to know this. She says, first of all, I'm a huge fan of Rosetta mission and StarTalk.
Aren't we all?
Oh, there you go.
There we go.
That just means you're smart, Josefina. That's all that means. I'm a chemist by trade, and I was wondering what the implications would be of a Rosetta finding that A, only left-handed amino acids were found on Comet 67P, or B, only right-handed amino acids, or C, a racemic mixture, i.e. equal amounts of both.
Okay.
Now, before you and Matt go totally geek boner crazy on this question, you're going to have to tell us what all of that means.
What it all means.
I have no idea what Josefina is talking about, but it's an opportunity for me to learn something.
Okay, so we'll kick off with the fact that we want to look for organic material in space. And I think this is kind of what the question's getting at. Are we looking for organic material in this comet? Well, yes, we are. There's quite a few instruments on the orbiter and lander that are looking for these features and trying to detect carbon molecules. Now, in terms of looking for anything more advanced than that, if we're talking DNA, I don't think there's anything that can look for that. But if we come back a step before we get to DNA, we've got amino acids, which form from carbon molecules. And these are what we would refer to as the basic building blocks for life.
Okay.
So we kind of need these to get life started, we think. And our bodies contain loads of amino acids. Right. And we found amino acids in space before. We found them in asteroids. Meteorites that land on the surface as pieces of asteroids, we found lots and lots of amino acids. So we know that the building blocks are out there. Now, with Rosetta, we're not looking for these specifically, but there are a couple of instruments that are trying to detect carbon compounds. Now, I'm going to pass over to Matt because he can now tell us a little bit about what some of those instruments have found, because it's quite recent research that's just come out.
Oh, we're getting breaking news here.
Yeah, it is, definitely. So,
Nice.
yeah, Matt, there's a couple of instruments on the lander that have found some interesting stuff related to the organic material.
Yeah, both Ptolemy, so Open University instrument, also COSAC from Germany, were focusing on this specifically. Now, from my knowledge, and now remember, I'm a plasma physicist, so this is on the edge of my comfort zone, as it were. I know that we did find a lot of organic material. We could see that organic material. This is carbon-based material. The comet is really, really dark. It's very, very black. It reflects less than 5% of the sunlight that is input to it. So that really tells you that we have this very carbon-rich material on the surface. And as I was saying before, this ground level taste of the comet was what we needed from Philae, and that's what it got, even with the bouncing across the surface of the comet. And we had samples. Well, I'm trying to remember actually. I think COSAC. If up is the top of the lander and down is the bottom of the lander, I think COSAC was pointing down and Ptolemy was pointing up.
Exactly, yeah.
And so they kind of got this fractional sample of the atmosphere in the near surface. So COSAC actually got the dust that was kicked up from the surface and really got some nice nitrogen and carbon-rich compounds. I think there were 4 compounds that have never been seen before, and these are associated, I think, again, on the edge of my memory, with ribose, which is a sugar which then is, again, a building block of, or can be connected to amino acids and DNA. So that was seen on the bottom with COSAC, and on the top it was more of the coma material, more of the gaseous material that we were seeing in the atmosphere. And so we were able to see that and distinguish the different components from the lander.
Yeah.
On the orbiter, we have ROSINA that's got this fantastic array of instruments that do mass spectrometry and can sample material there. They've been looking at we've had record or instances of seeing different, we were talking about it before, the methane, etc. And we hope to get some more information on that soon. That's all I'm.
Oh, we have an insight here.
Right.
This is exciting.
This is cool.
But it's great because
related to this.
Okay, well, it's great because all the different instruments have done slightly different things, and actually they don't all necessarily agree, which is quite interesting. So
now, what do you mean by that? Because that sounds very contradictory,
worrying, yeah,
and it sounds worrisome. What do you mean that they don't all particularly agree?
Well, basically, because they're measuring different things. As Matt was saying, the COSAC instrument is measuring the composition of basically the rock of the comet,
right?
Because it's right at the surface.
Right.
Whereas the Ptolemy, so it saw nitrogen compounds and things,
right.
And then Ptolemy was measuring the gases around that, so it didn't actually measure any nitrogen. We don't really know why. Maybe the nitrogen wasn't kicked up high enough so that Ptolemy didn't get it into its mass spectrometer. But it measured lots of carbon dioxide. So we know there's a lot of carbon there.
Right.
They agree on some things, but then you've got ROSINA, which is way outside of the comet, looking at the coma and everything outside of that. And that's, obviously got different results, but I'm sure they'll be complementary. It's just you're looking at different parts. It's a complex
So it's not that they
system.
don't agree, it's that they're measuring different things.
Measuring different things,
okay.
yeah.
And those things don't always just perfectly mesh.
No, we have to put all of these little bits of data together and build up our picture of the comet because it's an active system. We've got to understand what it's doing as it goes towards the sun, how it's getting heated up, and how that's affecting the different molecules on it.
Okay.
So, yeah.
But the one thing that we can say, Matt, is that it's not broken. So it's not like it's measuring different things because it's not working.
No. One thing that I recall is when I
want to know is, are you wasting my money?
These are highly intricate instruments, but one has to recall, and I remember talking to a colleague of mine who was an undergraduate with me when I was in Liverpool University, and he remembers mass spectrometers being as big as a room. And I think, Natalie, I remember talking to you at OU with these big machines.
Yeah.
Now, you can't fly something that big in space, so you have to miniaturize the instrument. And I'm not saying the instrument, well, it has less capability. It's still a fantastic instrument, but you've miniaturized it. So it has a limited capability compared to something on Earth. So there's a limitation in what you can do. So you have to make assumptions on the observations that you're making. So the spectra have, when you're looking at a mass spectrum, there are bumps and wiggles and lines everywhere that could be various different compounds that this thing's sniffing. And you have to make assumptions based on your understanding in general of what they are. So it's really you're doing the best you can with an instrument that's been packed in from a room-sized instrument to something as big as or smaller than a shoebox.
Yeah.
Wow.
It is amazing. And because we need the instruments to be light,
right?
Because we've got to launch them into space.
Exactly.
And we need them to be relatively simple because we don't have a human to go up there and run it.
There's no maintenance for this.
Anything goes wrong, there's pretty much not anything you can do. You know, you pre-program sequences that it will run and the computer programs and it runs them. And if anything goes wrong, there's just nothing you can do about it. So these things have got to be simple, but it doesn't mean they're actually simple. You know, they're still doing very complicated science.
It's physicist simple.
Yeah. It is.
Yeah, it's like, you guys simple is like most people's, I just died of a stroke thinking about it.
And they also have another version of the instrument on the ground. So the scientists, have been waiting 10 years for this to get to the comet. They've actually been able to perform lots of calibration experiments on their version that they've got maybe in a chamber that's kind of like comet conditions. So it's in a vacuum and stuff. And they can actually run sequences on it to test how that instrument's going to work in space.
Okay.
So that's important as well. There's a lot of work that goes into it.
And so, Matt, when you're running these calibrations, do you then take that and make an adjustment to the data that you receive from space and adjust it accordingly to the calibrations that you run here on Earth?
Well, yeah, that's what you do. And actually something that was done based on the Rosetta measurements. So the Rosetta, for this was for ROSINA, they made measurements with their highly advanced instrument, and they were able to actually go back to data that was taken 30 years ago from the Halley mission.
Wow.
The Giotto mission at Halley, and readdress some of the spectra that were taken there with the instruments there and reanalyze them based on the measurements we have here. So in a kind of cross spacecraft mission calibration as well. So all of this data you can go across and cross compare and improve your measurements.
That is fantastic.
Yeah.
I mean, that's really fascinating stuff. Well, Josefina, let me just tell you, that was an incredible question that you gave us.
Yeah.
Because, I mean, who knew that we would get all of that out of this one question? Really fascinating stuff, and I learned some things there too. That was really great. Wow, I feel like I'm one of the Cosby kids. You say, oh, look at that, I learned something too. You don't even realize. Okay, all right, I'm going to stop that right now.
Just to jump in there, because the Josefina had asked about chirality. That was one of the measurements we wanted to do on the lander with COSAC, and that's the only instrument that could have made this measurement. And this is to look at the hand it's basically the symmetry of the molecules. You can either have left-handed or right-handed. And again, it's this connection with the material we see in space and how is it connected to life on Earth. And certain things on Earth have a particular chirality and others have a different chirality. And by looking on the comet, we'd be matching and seeing if there is a match between the two. So are the amino acids on the comet left-handed or right-handed, or are they both? And vice versa for other things, sugars and DNA and this kind of thing, and trying to see if there is a connection with those that we're finding on Earth. The problem is, with the lander, we weren't able to get a sample in the ovens, which was necessary to run a specific part of the COSAC instrument, which was to examine chirality. So without that, now that the lander is most likely not going to function anymore, we have not been able to carry out that measurement. So I just wanted to get back to that part of the question.
Oh, nice.
Yeah,
all right.
It still needs doing.
Still needs doing.
More missions.
Well, there you go, Josefina. That's I believe we have thoroughly answered this question from top to bottom, in and out. This honestly, this was answering this question was like a cosmic proctology exam. So let us move on.
Okay.
Look at Matt laughing.
I'm gonna have to quote you on that.
This is Sven Rosandik, or I don't know how to say his last name. I'm sorry, Sven Rosandik.
Where's he from?
I don't know, but with a name like Sven, I think he's a Viking.
Yeah, I think
so. So this is what Sven says. He doesn't tell us where he's from, but he's writing to us from Facebook. This is what he says. Would it be possible to land a spacecraft such as Rosetta on a comet and then stay in contact with it so that every few years it sends us more information? And so I'm going to add on to that, with that in mind, would we be able to land on a comet just say for instance, like Halley's Comet, which we know leaves our solar system, goes, and then comes back.
Yeah.
Will we be able to do what Sven said and then get readings from that comet wherever it goes and then gather those readings when it comes back to us?
I mean, kind of, and there's a lot to say with this answer, really. It's more that, yes, you could in theory, but the problem is when comets get really far away from the Earth and the Sun, it gets really cold.
Okay.
And communications take forever. So you're going to have to put that spacecraft into hibernation, most likely, like we did with Rosetta, as it was trying to catch up with the Comet 67P. It got very far away.
Right.
So it had to go into hibernation, go to sleep for a couple of years. So you could do that. You need to leave a little bit on because it needs to stay warm in order for the instruments to actually kind of work. Otherwise, they're just going to completely freeze and be broken. So if you could do that, bring it back in, turn it back on. Not always that easy. When we had to bring Rosetta out of hibernation, that was stressful because we didn't know it was going to turn back on. It was like, Matt, I mean, you can probably add something to this. I mean, I was there watching it on, the internet feeds, but I was stressed, and we got the signal and it took longer than we thought. And I mean, it must have been, but were you in mission control for this?
Yeah, I was. It was fine. It was
fine. He's like, I play it down. There's been so much happening since then, but I was like,
piece of cake.
Yeah, it's all right.
Yeah, nothing
there
to
was
it.
a level of stress, but I mean, we put the best people had designed this to happen, so we've done the best job of getting it out of hibernation.
Yeah.
So, and as you said, it had been delayed a little bit, but in the end, it did come back. In fact, when you talk about stress, the one guy I remember who looked the most stressed was the person that was involved in writing the software for the hibernation exit, and he looked he was the most relieved person in the room.
I can imagine. Yeah, that would be, big
Because
moment.
at that point, it's all on him. Yeah. And everybody's going to point their finger, even though they're not physically pointing a finger. They're just like, yep, Thomas, totally fucked.
Yeah. I think I would have fainted when that happened. I would just been like, oh my goodness.
It's the truth. It's just like, you know what I mean? It's like Alex Rodriguez in the bottom of the ninth and the bases are loaded and you're up to bat. And when you strike out, people are just like, what a waste of $30 million. Nobody says like, it's okay. Everybody says it's okay, but what they're really thinking is, dude, you just wasted all of our money. And that's what, Thomas, thanks for the program. You screwed us all.
Yeah, so I can imagine that is pretty stressful. But yes, so in theory, Matt, I think, we're running out a little bit of time on this segment.
Are we running out?
But I think it's kind of possible, but it probably isn't the most important thing for us to be trying to do, because it's better to go to an asteroid or a comet and measure it and then get done with. Theoretically, I would love to bring samples back. That would be the best thing.
So it's more important to get on that comet as it's traversing out close enough to our solar system.
Yeah.
Land on it, get something off of it.
And come back.
And bring a physical sample home.
Exactly, which is what we're trying to do with some of the future asteroid missions. Okay, so we're going to wrap it up there for this section, but we're going to be right back. Some more cosmic queries when we come back with StarTalk All-Stars. Welcome back to StarTalk All-Stars. I'm Natalie Starkey. Still here with me is Chuck Nice and Matt Taylor from the European Space Agency.
Yes.
We're going to carry on with some more cosmic queries.
More cosmic queries, inquiries from the internet. That's my new song.
It's lovely.
Yeah, my album drops on Tuesday. Thank you. All right, here's the deal. I lost the question I wanted to. Here it is.
Okay.
Graham Woolley. Graham Woolley wants to know this. Why are plutoids made of different material than comets? Their origins are both trans-Neptunian.
Oh, wow. Okay. Lots of
This is a guy who...
Yeah, he knows what he's talking about.
This is a guy who read an article in Scientific American.
I think so.
I'm telling you right now. He knows his stuff. Okay.
Okay. So let's break this down a little bit. We've got the Kuiper Belt, or the Kuiper Belt, however you want to say this.
You know what's funny? Of course, doing this job here, I get to talk to a lot of scientists.
Yep.
And I still don't know if it's Kuiper Belt or Kuiper Belt.
I think it's...
Because I hear so many of you say it both ways.
I say Kuiper.
You say Kuiper.
I do.
Matt, what do you say?
I think I oscillate. I think it's Kuiper.
You're Kuiper?
I think it's Dutch origin. So
okay, so yeah.
Okay.
So Neil says Kuiper, you say Kuiper, Matt, you say Kuiper, but I know several physicists who say Kuiper.
Yeah, I think that's what Matt said.
Yeah, is Matt Kuiper too?
so.
Yeah. So
I think I'm in the middle somewhere.
always the politician, Matt. Look at you, the diplomat.
I do both now.
Right. All right, go ahead.
We have the Kuiper Belt. This is kind of way out past Neptune in the solar system. Not as far as the Oort Cloud. We also have comets, but the Kuiper Belt is important. There's a lot of comets there.
Right.
It's also where kind of Pluto happens to be. So we've got objects like Pluto. Now, the difference is that we've got objects like Pluto that are around and contain a lot of ice, but seem to look a bit like a planet. That's why Pluto used to be a planet. Unfortunately, no longer.
Neil killed it.
Yeah, he did.
Right.
Yeah, he killed it.
Thanks, Neil.
Then we have the comets, which are the remnants of the very earliest parts of the solar system, the remnants of this dust cloud that we started with.
Right.
They also contain a lot of ice.
Right.
Now, we still don't really understand where all of these objects came from and exactly where they formed. Now, it's thought that we've got the Kuiper Belt, which is closer in, and the Oort Cloud, which is further away. We actually think that the Oort Cloud comets formed closer into the sun than the Kuiper Belt initially. And actually, they were so close to the sun that they kind of interacted with some of the inner planetary bodies and were kicked way out of the solar system.
Okay.
So when we see them coming in to the inner solar system occasionally, and we can look at them with telescopes and even go to them with missions, we actually see their particular composition. And when we measure the ones from the Kuiper Belt, they're different. But then we've also got the plutoids, which are another kind of family of objects out there.
Right.
The problem is they're all really far away and we don't go to them. You know, we've now, with the New Horizons, of course, we have been out this far.
Right.
And, well, some other missions have been that far as well, but specifically to look at these objects. So we're still learning about them. So I kind of can't answer the question that well. Matt, do you have anything to add? Because it's like we need to just learn more about these things.
Yeah, I think that's the thing. It's trying to constrain what you call a particular thing. And that's the thing. You start associating names to different objects. And, well, as you're alluding to, the Kuiper Belt and the Oort Cloud, when you look at 67P with Rosetta, that's a Jupiter-class comet, likely from we call it a classic and a true Kuiper Belt object. We have other Jupiter-class comets that we've observed that have a completely different composition if I relate to the deuterium to hydrogen ratios, which are kind of a proxy for this whole where they formed with respect to the sun in the early solar system. And what we found with Rosetta and also the Halley measurements with similar to 67P, showing a broad range of these D to H ratios for a particular class of comets, which again mixes up your understanding of the dynamical processes and the evolution for those particular bodies. So it's a bit of a difficult mix. And when you say, right, okay, Kuiper Belt, Oort Cloud, that's the comets, and then we've got the asteroid belt, but then in the last 10 or so years, people have started talking about main belt comets as well. So this classification of these small bodies in the solar system is becoming more and more diverse.
Right.
And I think they're all an intermix of everything. It's just their evolutionary processes or their evolutionary track has been very different. And by doing Rosetta, by doing New Horizons, by doing asteroid missions, we try and get a better idea of one particular asteroid and how that fits into the global picture and all the massive simulations we're doing. So it's not an easy one to answer. We are learning.
Yeah, we are. And I mean, Matt mentioned their D to H ratios, which are really important for understanding these objects. And we can actually measure that in kind of on the object, if we can get to it, or we can measure it with telescopes. Now, you're then comparing measurements made by different kinds of instruments.
Yes.
But what we're looking at is essentially the composition of the water or ice, water ice, or liquid water, mostly ice.
Right.
And we're looking at the heavy type of hydrogen, which is deuterium, in relation to the lighter type, which is hydrogen. And we're literally just looking at the abundance of those two things. And that tells us a lot about where we think that formed.
All right, so let me ask you both this, based on what we just talked about there. What would you rather have? A physical rock sample of an asteroid or a chunk of ice from a comet? So which one would you rather analyze?
Matt, you can go first. Which would you prefer?
We've had asteroids, so is comet. We have to have a sample of a comet in a lab on Earth.
As ice, though. That's
as ice.
You've got to
My
bring
part.
it back.
That's my thing is before the
back in a deep freeze.
In a big freezer.
Big freeze. So now let me ask you, because that's a huge. Of course, we all see what happens when comets come into the solar system. They get close to the sun. They start to.
They do.
And then they just kind of flame out.
Yep.
So now, how? I'm sure this is a stupid question, because if we knew it, we probably would have done.
Stupid questions.
There are no stupid questions.
No.
I totally disagree with you. When they say there are no stupid questions, I'm just like, you have not heard what I'm about to say. So no. Is there plans or a contingency or anything to actually break off a chunk of ice and get it back here? But how would you do that but how do you keep something cold enough to get it back to Earth so that it doesn't evaporate and disintegrate once it gets, on the journey?
It's a massive challenge, but it is something that most sample-based scientists are actively thinking about and trying to work on. Actually, the first place we want to try this is on the moon, because we know we've got ice deposits at the poles of the moon.
Oh.
It's relatively close to us. We know we can get to the moon. We've done it lots of times.
Yes.
And not saying it's easy, but the challenge will be trying to collect some of these ices from the poles and bring them back as ice. Because you can analyze there, you can go and analyze them with an instrument on the moon. But ideally, we want to bring stuff back because we've got the best instruments on Earth. We've got the people, we've got the instruments, and we can make the best measurements. So,
and the best instrument of all is the tongue. And you just have a little sip of the space water.
See what it's like. Yeah. So, this is what we're trying to do. I think that's the first step. And then, if we could bring about ice from a comet, that would answer some major questions about some of the solar system formation. Now, I say that, but the problem is all the comets, as we kind of alluded to, are all different. And although there's going to be groups of comets that are similar, going to one comet isn't actually going to answer all the questions. It's going to help us, but we need to go to lots of them, which is a bit of a problem because
you are
it's
very
expensive.
greedy, Natalie.
I am greedy.
Very greedy. Look at you. We haven't landed on one, and you're like, oh, we got to get to 15 or 20 at least.
Actually, just jumping in there, in 1987, when Rosetta was first thought about, that was actually a comet sample return. That was what it originated as. It was supposed to go to a comet and bring a bit back to Earth. And that was shown to be it was what we did anyway was quite extravagant. I think they were kind of going, look, just cut that bit because you're going crazy now. A lander, but not a lander, then come back again and then fly all the way back. It
effectively makes it like 2 missions, so effectively doubles the cost, because not only do you have to land, you've got to then launch again and get off fairly easy on a comet because there's not much gravity.
However, the very encouraging and positive thing about this is we're halfway there.
We are.
We got the first half of the mission done, thanks to Matt and his team, right?
We had to prove with Rosetta that we could land on one in the first place. So, this is the thing. When we went to the moon and Mars, we did lots of orbiters, we did lots of surveying to decide where to land. Right. Whereas with Rosetta, we were doing all of this in one go. In 2014, when we arrived at the comet, we saw what it looked like for the first time. And then we had to land on it within 6 months.
And that's important to stress.
Anyway.
Yeah, that's really important to stress. We'd never seen this thing before. The moon, we've seen it. It's right there. We can just look at it and we kind of know what it looks like on the surface, what it's made of.
Sweet.
But comets, we have no idea. We've never seen it before. So.
Fantastic.
Yeah.
Well, Graham Woolley, was a great question,
it was,
my friend.
very good.
Very nice. We got
just jump in quickly.
What's that?
To add one thing.
Go ahead.
Go ahead, Matt.
Sound like to try and bring this all in a little bit that we don't know anything about because we've got so many comets. One of the key things with Rosetta is, and as you alluded to about remote observations, the thing that we can see these comets from the ground on Earth and also space-based and Hubble and other measurements like the Herschel Space Telescope, etc. By having Rosetta sitting there next to a comet, and when we're observing it from the ground, it's kind of like a bootstrapping, a calibration of the ground-based observations. So when we do that cross-comparison between what we see in situ with what we see on the ground for 67P, we can then take those measurements and apply them to all the other cometary observations that we've ever made and will make in the future. So it's a nice calibration effect
so it's almost,
that then expands everything.
Almost like we've been to more comets in that way.
Right, exactly. So so everything that we've already observed, now we can re-observe through the eyes of
this new
of Rosetta and 67P.
Yeah.
Fantastic. That's great stuff.
Point, Matt. Yeah.
That's great. Great point. Great point. All right, Graham Woolley, way to go, man. That was a great question. I love it when these people really think very deeply about the questions they ask. Let's go to Maria Macario.
Oh, okay.
Maria Macario, who writes to us and says this from Facebook. When Rosetta flew by the asteroids 21 Lutetia and 2867 Steins, what relevant information did it gather on them? P.S. I hope Chuck Nice doesn't mispronounce my name.
Oh.
Just kidding. I'm sure he will.
Well, she didn't say how we were to pronounce it.
Well, this is true.
We need phonetically.
I screw up everybody's name, so, you know.
It sounded good to me.
I hope so. And guess what? If I said it wrong, you should change your name to Maria Macario. So let's talk about these other two asteroids that she said on the flyby, 21 Lutetia and 2867 Steins.
Yep.
Were we able to get any information from those?
Yeah, we got loads of information. So we got loads of images of these things. Never really seen them before. So, you know, beautiful images of asteroids up close, fairly close anyway. And I think also, Matt, am I right in saying we turned on some of the instruments just to have a little test to see that they were actually going to work eventually? And kind of sniffed, let's say we sniffed the asteroids. That's right, isn't it?
Yeah, but I think we also ran some of the dust instruments, but they proved that there wasn't really a coma around these objects. So yeah, there were null results, which are results.
Yeah. So yeah, definitely. We got lots of information. So there we go. Yeah.
All right. There you go, Maria.
No, they were like bonuses to the puzzle because
that was icing on the cake.
On
right?
the way.
That was on the way. Exactly. Right. It's like it's like car sex on the way home.
Oh my goodness.
Yeah, you know.
We have time
for
a very short question.
Oh, really?
Yeah.
I love when I make a joke and you can't see it, but Matt was laughing.
And I'm just like, let's move
cringing.
on. I'm like,
it says like car sex on the way home. You're like, oh my
Next
God.
question.
Matt is cracking the hell up. I love it. I love it.
Okay, really quick.
All right, let me find a quick question. Quick question. All right. This is Matt Eli from San Antonio, Texas, coming to us from Facebook. Why is the comet surface fluffy?
Oh, no, I want longer. I'm going to have to make this really, really short. Okay, so the comet is essentially made of this early gas and dust from the solar nebula and ice, and it's kind of held together. So this real dust is like the fluff of the solar system. It's not made it into a planet. So the planet's kind of consolidated all this dust and made it solid like the planets. But in the comets, it didn't, because it was kind of a low energy environment out in the comet formation zone. So this stuff stayed fluffy, a bit like candy floss kind of thing. So the surface of the comet is very much fluffy. As it goes via the sun, it loses all its ices as it's going, and it loses a lot of material. This dust kind of comes off. It dehydrates the surface of the comet. So
because the surface of the comet was never compressed to the point where it could be bound tightly.
Exactly. So we have a fluffy surface, and I love this dust. This is what I do. But
and the other answer, Matt, is cosmic fabric softener.
Okay, and that's interesting. Okay, so we are completely out of time, and I wish we'd had longer for that.
Yeah, that was a lot of fun. I got to tell you, that was a lot of fun.
I think we've learned quite a lot. I've learned some stuff as well. It's good.
Yeah, I'm serious. It was super cool to have Matt here because I got to tell you, having somebody who was actually a part of the mission.
Yeah.
I mean, I really learned a lot. This was fantastic.
We're very lucky to have him. But thank you so much, Matt. You've been fantastic as always, and I love your shirt, so that's cool. Didn't mention that. But that's all we have time for. So, well, thanks. Thanks for joining us.
Thanks.
Had good fun. So that's all we have time for today. I want to thank Matt Taylor from ESA, who's joined us, and Chuck Nice. And that was StarTalk All-Stars. I am Dr. Natalie Starkey.
This is StarTalk.